Hi, welcome to first. There is if we have this thing, all the mass a lot of energy. Let's check you all what is how much meter that you can give. 1 joule of energy means that let's say we can convert all the mass of the body mass using M is my weight, your weight, C is the speed of light, and we will punch into the equation the number. This will be the number. This is a very big number, 4.5 times 10 power of 80, which means that if we can convert all of our mass, we can take whatever for this 4.5 times 10 power of 80 meters. That's very far away. This is your first task. You want to ask the you want to give instructions, but is to prompt the AI and what will the output from our prompt from here. The question is, assume that is a planet. We can choose either one of the planet. Let's say we choose the Venus. That would be the second planet, and the planet, the closest planet. Assume the planet Venus is on the face, is on the Earth's surface. The planet softly drop on the Earth's planet. Now, I want to save the Earth. I don't want the Earth to be burdened by so I want Venus for my how much energy that I need to live for one. Next, if I can convert all my weight to the energy, then how much should I so that I can lift Venus up for 1 meter? We're going to prompt but.google.com go to this website and then see the question. Assume planet Venus is on the Earth and then show me the option. So after around 30 seconds, go back to your solution. What is the energy that required and what would be my weight if I can convert and lift Venus for 1 meter? Google Bard will tell us what will be the calculation so you can check how much should you weigh so that you can save. The energy is measured in joules per J. Energy also brings the meaning of ability of doing work. A work is defined as the force times the distance. Means that we can interchange between the work and the term energy. If we have the case that we are given the force and we have the distance, we can use these two elements to represent the energy in other form. Energy, if you want to categorize them into two big areas, we can say that one is the kinetic or the movement energy, the energy that we can see, we can hear, and we can sense. The second will be the potential energy. The energy is stored, we cannot see, but we know it is exists. When we split the energy into two groups or two categories, the kinetic, for example, the sound, we can hear it. The thermal, we can sense it because it's very hot. We have the wind, we can see uh, the wind, the condensed air there is spinning, and the other examples. While for the potential energy, for example, the gravitational energy, we put a big stone on the table, bam, here. We know it is safe at the moment because the stone is not moving, it's static. However, at one point, the table will break down. And then we know that the energy is doing something and it is so powerful. The stone drops down and hits our foot and we will feel so painful. Besides that, we have the electrical energy, we have the nuclear energy. All this energy cannot be seen. However, we know it exists. Energy will preserve itself. It means that inside a closed room, let's say BLK10, nobody goes out, there's no sound travel out, there's no light penetrate through the room here. Everything is keep inside BLK10. At 9 o'clock this morning, somebody measured and found that the total joule of the energy is 50 joule. Even after 8 hours, when we come back and do the measurement, it will still be 50 joules. It might be the different form of the energy, but at the end, the total value will be the same. For example, we have somebody riding the bicycle here. This guy already eaten his breakfast, so he contains certain kind of the chemical energy. Once the chemical energy had been converted to the kinetic energy by his body protein, the ATP, the cells, those kind of the metabolism process. So he start to pedal the bicycle, and the bicycle will be having the kinetic energy because it's spinning. So this kinetic energy will goes into the dynamo here. So the dynamo, they have the electrical and the magnetic components that turning the kinetic energy into the electrical energy. Once this electric goes and hit the points of the lamp, it will turn into the light. Let's say the guy is providing 10 joule of the energy. At the end, assume there's no energy loss in between there. There will be 10 joule of the light energy produced. This is the principle of the energy conservation. This is task number 2, 5.2. You want to visit, there's a website called thequara.com. Type this link here, quara.com/whatisenergy. There'll be many articles about what is the energy. Choose one of the article and then write down who is the author, when was the date. Let's say the article was written year 2019, so just write down the years. This will be a long article, maybe it contains 200 words. You want to summarize it into 30 words only. Do the summary of the article, and later on, from your summary, you translate into one image. One of the example is by the Kusha Aurora. is written year 2020. It says that energy in physics is the capacity for doing a work. It may exist in terms of potential, kinetic, thermal, electrical, chemical, nuclear, and other various forms there. So later on, you do the summary into 30 words, and also your 30 words will be represented by one image. Just now, we have many kinds of the energy, many forms. For today, we want to focus on three. The first one will be the kinetic energy. Kinetic energy says that this energy is associated with the motion of one object. When there's a car is moving, we say that the car you contain the kinetic energy. When there is a ball flying through the over the field there, the football field, we say that, oh, soccer ball, I see that you have the kinetic energy. As long as one object is moving, it contains the velocity, we'll say that, okay, object, I know you has the kinetic energy. What would be the formula to represent the kinetic energy? This would be the formula to find what would be the value of the kinetic energy of one object. It depends on the weight of the object and also the velocity of this object. It equals to 0.5 times the weight, the mass, and the velocity at that point, v squared. The second popular energy with the formula would be the gravitational potential energy. When we have a big stone, we load this stone on the table. We put the stone on the table, and our table is 2 meters high from the ground. M will be the weight of the stone. Let's say the stone is 10 kilograms. G would be the constant for the gravitational acceleration. H would be the distance between the table and the ground. That will be 2 meters. So we can know what would be the value of the gravitational potential energy of these stones. The third popular formula for the energy would be the spring energy. When we compress a spring, it can be represented by this formula. 0.5 times the K. K would be the spring force constant, and X squared. X would be the how much distance it is compressed. If we have a very tight and a strong spring, the K would be a very big value. If we have a very soft spring here, our K will be very small. We're going to look at one of the exercise to relate between the gravitational energy and also the work. There is a 60 kilogram person jumps onto the floor from a height of 3 meters. So this is the guy, and he is 3 meters from the ground. So he jumps and then he lands. Everything is straight except for his knee. There will be a 0.5 cm compression at his knee sponge there. Now we want to calculate the total force applied to his knee joints, two of his knee joints. The total force. When we go back to the conservation of the energy, the before energy will be the same value to the final energy. So the before energy, when we ask this guy, what kind of energy that you contains, he'll say that I'm doing nothing, I'm not moving, I only have the potential energy, that is the gravitation energy. Before Everything is about the gravitational energy. It equals to the mgh. And then after the event happens, we see the only thing changed will be the compression at his knee joints there. His knee joints compression. So this will be the work done by his knee, will equals to the F times the D. When we merge this before and the after through the principle of the conservation energy, the mgh will equals to the F times the D. We'll check one by one. M will be the weight of the guy. The value is 60 kilogram. The G is the gravity acceleration. There will be 9.8. H will be the height between him and the ground, 3 meters. F will be the force applied to his knee. That's the value that we don't know, the unknown. So we'll read that. D is the total distance done by his knee. That will be 0.5 cm. We are converting to the meters. It equals to 0.005 meter. So from this equation, we have only one unknown, that is the F. After the calculation, we'll have the F equals to 3.53 times 10 power of 5 Newton. This is the total force that applied to both of his knee joints. It's quite a huge force. So it's recommended we don't jump from 3 meters high. It's going to put a lot of burden to our knee joints. Question 5.4. This question relates those three popular energy equations. The first will be the spring and kinetic, and also the gravitational energy here. Let's go through the question. The spring is compressed for 4 cm. Not much, just 4 cm. And it has a force constant of 250 Newton meter. This is the K. The car is a toy car. That will be just 0.1 kilogram, equivalent to 100 grams. And the car is released from the spring. Assume there's no energy loss due to the friction. You want to find what would be the velocity when the car is at the slope 18 cm high. What would be the velocity of the car when it reached this point here? So the before, when we ask the car, what energy that you have? The car will say that, can you see I'm just compressed against the spring there? I don't have other kind of energy. Everything is about the spring. Everything is about the spring. So we'll write, okay, car, I know all the energy that you have is because of the spring. And after the event, the car reached the height of 18 cm. Then we at that moment we ask the car, what kind of energy that you have? The car will say that I'm moving. You say that, okay, car, you're moving. I know that you have the kinetic energy. At the same time, I'm moving to a higher height. That would be 18 cm from the horizontal plane. Now, guessing the car will now contain certain kind of the gravitational energy. This is plus, okay. Erase this one. Now we want to expand the terms. The before will be the energy due to the spring. The formula is half kx squared. The kinetic energy represented by this formula, half mv squared. And then the gravitational energy is mgh. We want to plug all the numbers into this equation here. We're starting by half, no problem. K will be the spring constant, the force constant of the spring, equivalent to 250. Newton per meter. X is how much the car was compressed at the beginning. It's compressed for 4 cm. Change it into meter equals to 0.0. We put down the half. M is the car weight is equivalent to 0.1 kilogram. We square that we don't have. M is the car weight 0.1 kilogram. G is the gravitational acceleration. H is the height between the horizontal plane and the new height, that is 18 cm. When we look at this equation here, there's only one unknown, the V. The V that we want to find and we don't know. At the end, the V will equals to 0.687 meter a second. Means that at this height here, we'll see that the car is still moving. When we ask the car, what is your speed now? The car will say that 0.687 meter a second. We look at the next concept that's called the power. When we ask the Superman, I know that you're strong and then you can lift a huge stone. Superman will say, yes, no problem with that. And suddenly the super baby comes and say that, oh, I can move the stone too. Okay, we agree with your statement, you can move the stone. Only that, who is having much more power? Is it Superman more power, or super baby, or we call super kid? Super kid do have much more power. It depends on one factor, that is, how much time does Superman need to take to lift the stone? How much time do you, super kid, need to take and to lift the stone? Assume that Superman just take 2 seconds to lift the stone, and then super kid takes 80 seconds to lift the stone. We say that super kid, you can do, but you have no power. What? Power depends on the time taken to complete the work. This is the formula to represent the power, equals to the work divided by the time. So we use the watt to represent the power. We will look at one example here. There is a guy who's running up a 3 meters high stairs, taking 3.5 seconds to do so. And his final speed is 2 meters a second. The before and after. The before, this guy is static, he's not moving. And at the end, he reached the height of 3 meters staircase. At the same time, he has the 2 meter a second speed. So the before, it seems there's no any kind of the kinetic energy. It's not moving. There's no like the potential gravitation energy because it's on the ground. There's no spring involved. So we guess that he's going to use all of his breakfast energy, that would be the chemical energy, to convert into the kinetic and also the gravitational potential energy. So he used all of his chemical energy to convert into the kinetic and the gravitational energy. We're going to check what is the total energy that he has at the after. At the after, there'll be two kinds of the energy. One is the potential energy and one is the kinetic energy. So the total energy after would be the half mv squared plus the mgh. Let's check one by one. We have the m. The m is his weight. Yes, 60 kilogram. V is his velocity at the after, 2 meters a second. Next, plus m is his weight. G is the gravitational acceleration. H is the distance between him and the ground. That will be 3 meters. So we will have a number here. This is the total work, the total energy that he has at that point. We want to find out what is his power at that point. It depends on how much time taken by him to complete this work. So later on, after we have the value here, we'll divide by the time, 3.5 seconds. It's going to produce us the power of 5381. So this power that it has. How to show that we have much more power? It depends on what will be the time taken to complete the work. To show that, wow, I'm more powerful, so what I need to do is to reduce the time for me to reach that point. Instead of 3.5 seconds, let's say I just take 1.2 seconds to complete. So I can show to the other people that, see, I have much more power. We'll go to the next task, 5.5. Your task is to watch a YouTube video, and then later on you want to suggest one improvement for this traffic turbine so that it can generate much more energy. Earlier it just producing 1000 watt. Now can you do some kind of adjustment, redesign it so that it can improve another 50% of the energy? We'll look at the video.
These buses are waiting to do what they always do: carry passengers along Istanbul's crowded streets. But one young engineer thinks these city buses should be doing double time. He's created a vertical turbine that turns the wind created by passing buses into electricity.
The wind hits the wings and makes them turn. Mechanical energy is produced and becomes electric energy via the alternator below. There is a battery under the turbine and we store the energy there. If it becomes productive, then we plan to build more, and we will evaluate how to use the electricity we produce.
He hopes in the future, each turbine will produce enough electricity to power a home.
Our target is to produce turbines that produce 1 kilowatt of energy per hour. It is a prototype right now, but it will not stay like this. Its structure and shape will change. If it runs for 6 hours, each turbine will provide enough electricity to light a house for a day.
With only the first phase of testing complete, he's still a long way off from making any money. But Devchi plans to continue improving the design's efficiency.
This locally produced wind turbine is a surprising source of renewable energy. And with low production costs and no shortage of cars or buses on the road, you may well see them popping up on a highway near you. Osman Lone, TRT World, Istanbul.
You check the eCampus for the submission instruction. If you have anything, you can WhatsApp or email to me. Okay, bye bye.